In this video, we're going to introduce the 6 trigonometric functions as associated with the angles in a triangle and then the sides in a triangle. So specifically, we're going to focus on right triangles. So we define a trigonometric function based on the sides of a right triangle and how they relate to a given angle, specifically one of the two acute angles in the right triangle. So the right angle, of course, is going to be the 90-degree angle in the triangle, and the other two angles will have to be acute angles. So a trigonometric function, what we're going to call a trigonometric function, is going to take an angle as its input, and then the output is going to be a ratio of two sides in relation to that particular angle, whichever of the two acute angles we've chosen. So we have 6 standard trigonometric functions. The first one is called the sine function, and then we also have the cosine function, and then the tangent function. And then closely related to these three, we have the cosecant, secant, and cotangent functions. So each of these functions also has an abbreviation. So whenever we want to use these functions, we have an abbreviated version of each of their names, and those will typically be what we use as opposed to the full word sine, cosine, tangent, cosecant, secant, or cotangent. So we have a right triangle over here. Again, we have a right angle, 90-degree angle. We're going to choose one of the acute angles, and we're going to define the sides in relation to that particular angle. So let's choose this bottom angle here. So I'm going to label the angle, and we're going to call this angle theta. So we typically use Greek letters to represent angles when we're doing trigonometry. So in relation to this acute angle, we can label the 3 sides of the triangle. So the 2 sides here, we call those legs, and then the long side, the one opposite the right angle, is what we call the hypotenuse of the right triangle. Now the legs specifically, the way we label them depends on which acute angle we're referencing. So if we're referencing this acute angle, then the leg that happens to be incident with that angle is what we're going to call the adjacent side of that triangle. So if it connects to that angle and the hypotenuse, which of course we can label, I'm going to label that as HYP, that's our hypotenuse. The other side that is incident with that angle is what we will call the adjacent side. So it's adjacent to this acute angle. And then the side across from the angle we've chosen we'll call the opposite side. So it's opposite to that angle. Now one thing to keep in mind is how we label these 2 sides specifically is going to depend on which of the acute angles we've chosen. So if this is the acute angle we're looking at, the side incident with it will be the adjacent side, and then the side across from it will be the opposite side. If instead we chose to look at this acute angle, well, this now becomes the adjacent side, and this becomes the opposite side. So how we label the individual sides depends on which of the 2 acute angles we're looking at and which one we want to apply these 6 trigonometric functions to. So if this is our acute angle in question, this will be the way we label our triangle. So each of these 6 functions can be applied to this particular angle as an input. And the way these function outputs are defined is as a ratio of a pair of the sides in this triangle. So the sine function, if we want to apply the sine function, which we'll abbreviate as SIN, to an input of theta, the sine function is defined as a ratio of 2 sides. Specifically, the sides will be the opposite and the hypotenuse. So sine is defined as the ratio of the opposite side over the hypotenuse. And again, opposite is going to depend on which angle we're talking about. So if we're talking about this angle, this will be the opposite side. If we were talking about this angle, this would be considered to be the opposite side. So sine is defined as opposite over hypotenuse. Now the cosine, if we apply the cosine function to this acute angle, cosine is defined as the ratio of the adjacent side over the hypotenuse. So the adjacent side length over the hypotenuse. And then tangent, which we'll abbreviate as tan, tangent of theta, is defined as the opposite side divided by the adjacent side. There we go. So we're going to think of these three as the fundamental trigonometric identities, or not identities, excuse me, functions. The other three can be defined as being closely related to these three fundamental ones. So cosecant, which we're going to abbreviate as CSC, cosecant of theta, is going to reverse sine. So the cosecant of theta will be the hypotenuse divided by the opposite. Hypotenuse divided by opposite. Secant of theta is defined as the hypotenuse over the adjacent. And then the cotangent of theta, which we'll abbreviate COT, the cotangent of theta, is defined as the adjacent over the opposite side. And these are going to be the only 6 ways we can take ratios of sides in a right triangle. So these 6 trigonometric functions and the ratios that go with them are going to give us all the different ways we could choose 2 sides in the right triangle and then combine them together in a ratio. So you will have to have all of these memorized, which seems probably like a lot of work right now. I promise you will use these so many times that you don't even think about it. But for now, this is going to be a good mnemonic device you can use to remember, specifically the values for sine, cosine, and tangent. So the so, ca, toa mnemonic is going to give you the ratios for the sine, cosine, and tangent. So S stands for sine, C for cosine, and then T for tangent. So sine is defined as the opposite side divided by the hypotenuse, so. Cosine is defined as the adjacent side divided by the hypotenuse, so ca. And then toa, tangent, is defined as opposite over adjacent. So this is going to be a good tool to help you remember what those 3 ratios are while you're starting to learn these. Now cosecant, secant, and cotangent, notice those aren't included here. There are going to be other ways to remember what cosecant, secant, and cotangent are, which is going to lead us to what we call a couple of trigonometric identities, different types of trigonometric identities. So based on how these ratios are defined, we can also define identity relationships among the trigonometric functions, among the 6 functions, particularly as they relate to sine and cosine. So the term identity, what does identity mean? An identity is going to be a relationship that's true for any input that it applies to. So we're going to define a relationship among the trigonometric functions, or a set of relationships among them, that's going to be true no matter what input we take, no matter what the angle is that we plug into the trigonometric function. And as it turns out, all of the functions can be related back to sine and cosine. So knowing as much as we can about what the sine and the cosine values are is going to help us in the long run, because it's going to give us enough information to determine any of the other ratios. So the first identities we're going to look at are called the reciprocal and quotient identities. So reciprocal means taking a fraction and then flipping it upside down. So the cosecant function is defined as the reciprocal of the sine function, and this is the way we would write that. So cosecant of theta is going to be 1 over sine theta. And it's worth mentioning right now, notice when I wrote the definitions for my trig functions, we use the same abbreviations, but here I've dropped off the parentheses around theta. That's going to be considered standard practice in trigonometry, just because it's going to save us a little bit of time. So when you want to write cosecant of theta, either you can write it like this, with the parentheses indicating that theta is the input into this function we're calling the cosecant function, or you can leave off the parentheses and it's just understood that cosecant is applying to this angle theta that's right next to it. So we're going to get in the habit of writing it this way just to save some time, but keep in mind this notation is the same thing as this notation, which is a little bit closer to the function notation you're used to seeing. So cosecant is defined as the reciprocal of sine. And we can actually see that from the definitions. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite, well, they are going to be reciprocals of one another. So cosecant is the reciprocal of sine, and then in the same fashion, sine is the reciprocal of cosecant. So what that means is if you have one of these two values, if you know the cosecant of an angle, or if you know the sine of an angle, you know the ratio associated with that angle, then you can determine the other function just from knowing what that is by taking its reciprocal. Now, secant and cosine are defined in the same way. So cosine is adjacent over hypotenuse. Secant is the opposite, hypotenuse over adjacent. So we take the reciprocal and we have the other function. So secant is 1 over cosine, and cosine is 1 over secant. So again, if you know one or the other, that's going to give you enough information to find the reciprocal value. And then the same thing for cotangent and tangent. Cotangent is going to be the reciprocal of tangent, and then tangent is going to be the reciprocal of cotangent. So how does knowing this help you? Well, if you can remember SOHCAHTOA, which is going to give you the ratios for sine, cosine, and tangent, then all you have to know is which function each of those is related to. So sine is defined as the reciprocal of cosecant. So if you remember what the ratio is for sine, and you remember how sine is related to cosecant, then all you need to know is the ratio for sine in order to know the ratio for cosecant. And then the same thing for cosine and secant, and then tangent and cotangent. So these are what we call our reciprocal identities because they're going to take a trigonometric function and they're going to relate it to another one just based on this reciprocal relationship. Now we also have a couple of quotient identities which are specifically related to tangent and cotangent. So tangent is defined as opposite over adjacent. Another way of defining the tangent function rather than in terms of side lengths is actually going to be in terms of sine and cosine. Tangent is also defined as the ratio of the sine function over the cosine function. So if you take the value of an angle's sine and then also take the value of an angle's cosine and take the ratio of the two, that's going to give you the value for tangent. So this is worth verifying. These relationships are maybe a little bit easier to see just based on how we've defined the ratios. This one may not be as obvious. So let's actually prove that this is the case. So let's start with just the ratio of sine theta over cosine theta. So let's write this out to the side. So sine theta divided by cosine theta. Well, based on our ratios, let's actually write what those are equal to. So sine theta is defined as our opposite over hypotenuse, which I'm just going to write as O divided by H. And then cosine is defined as our adjacent over hypotenuse. So that's divided by adjacent over hypotenuse. So what we have here now is a complex fraction, fractions inside of fractions. Or alternatively, we can think of it as fractional division. So we're taking one fraction, dividing it by another fraction. Well, the way we interpret that in order to execute the division is by converting to multiplication and multiplying by the reciprocal of the denominator. So another way to write this would be opposite over hypotenuse times the reciprocal of the denominator, which would be hypotenuse over adjacent. We'll notice that common factor on the diagonal. And what are we left with? In the numerator, we're left with O for opposite, and in the denominator, we're left with A for adjacent. Opposite over adjacent is our definition for tangent. So that verifies that the ratio sine theta over cosine theta is, by definition, the same thing as tangent theta. So that's a verification that this identity is in fact true. The same kind of thing applies for cotangent, except imagine reversing this ratio. So again, the benefit here is if we know sine and cosine, then we can determine tangent, we can determine cotangent, and if we know sine and cosine, that's also going to give us information about cosecant and secant. So just knowing these two values is going to give us all the information we need about any of the ratios in our triangle. Okay, so let's look at one other type of identity that we can get just from these definitions, these ratio definitions. So we can also derive another set of identities from the Pythagorean Theorem. And we call these Pythagorean identities because they are related to the Pythagorean Theorem. So we have 3 different identities, and again, these are going to relate a pair of trigonometric functions related to our particular angle theta. So the fundamental Pythagorean identity is sine squared plus cosine squared of the same angle is equal to 1. And believe it or not, this is really just another way of expressing the Pythagorean theorem, just using these trigonometric ratios rather than using specific side lengths. So how could we verify that this is true? Well, let's write out what the Pythagorean theorem would look like in terms of how we've labeled this particular triangle. So normally we call our sides A, B, and C when we're using the Pythagorean theorem. Here we've called them adjacent, opposite, and hypotenuse. So if we were to write the Pythagorean theorem just based on how that right triangle is labeled, we know that the adjacent squared plus the opposite squared is equal to the hypotenuse squared. So this is just the Pythagorean theorem, again based on how we've labeled that right triangle. What I'm going to do now is I'm going to take all 3 terms, the 2 terms on the left, the 1 term on the right, and I'm going to divide them by something common. In this case, I'm going to divide everything by hypotenuse squared. Now, how do I know to do this? I know to do this because I know where I'm headed, but again, this is just a way of verifying the truth of this identity just based on the fact that we know the Pythagorean theorem is true. So what happens as a result of this? Well, a couple different things happen. So a squared over h squared, we could also write that as a over h quantity squared. In a sense, we're pulling out that exponent. And then o over h squared as well. And then h squared over h squared, well, the numerator and denominator are the same, so that division results in 1. Well, what is a over h? A over h, adjacent over hypotenuse, is our definition for cosine. And then o over h, or opposite over hypotenuse, is our definition for sine. So what we now have here is cosine squared theta. That's going to be the way we write a squared trig function. We write the square, or whatever exponent, next to the actual function label, and then we write the input. And then o over h squared is going to be sine squared theta, and that's equal to 1. So although these 2 terms are out of order, that's going to be equivalent to this first identity. So this identity can also be verified just based on the fact that we know the Pythagorean theorem is something we can follow, and then we can use those 2 ratios in order to define this particular relationship. Now we also have 2 other Pythagorean identities that are directly related to this original one. So if you were to take this original identity and divide each term by cosine squared, that will give you this particular identity. So imagine taking this identity and dividing all 3 terms by cosine squared. Well, sine squared over cosine squared, sine over cosine was another way of defining tangent. So sine squared over cosine squared would give us tangent squared. Cosine squared divided by cosine squared would give us 1. And then 1 divided by cosine squared. Well, 1 over cosine is secant. Remember, cosine and secant are reciprocals. So 1 over cosine squared would give us secant squared. So that's going to be another identity, but it's specifically going to relate the tangent and the secant functions. And then similarly for the last one, if we were to divide all 3 of these terms by sine squared, we would end up with 1 plus cotangent squared is equal to cosecant squared. So the benefit of knowing these identities is it's going to give us some versatility in how we actually determine the values for all the different trigonometric functions. So There's benefit here. There's also going to be benefit later on as we try to develop more relationships among the trigonometric functions and we start to create identities of our own just based on these fundamental identities. So now we need to do a little bit of practice actually finding values for our trigonometric functions. So based on an actual triangle with actual side lengths, how do we determine the values for these 6 trigonometric ratios, the 6 trigonometric functions? So it's going to be an exercise in, number 1, labeling a triangle, making sure we know what all the different parts are, specifically all the different side lengths are for our triangle, and then writing those ratios down. So here are our directions for the first one. So suppose that a right triangle has legs of lengths 4 centimeters and 7 centimeters. We want to evaluate the 6 trigonometric functions for the smaller acute angle, and then we want to rationalize the denominators if necessary. We'll come back to this direction and we'll talk a little bit more about that as we get there. Okay, so the leg lengths are 4 centimeters and 7 centimeters. So that means the sides other than the one opposite the right angle. So leg, leg. Now how we label the triangle ultimately is arbitrary. In this case we have one side length that looks longer and one that looks shorter, but ultimately it's just a matter of labeling. Now because we have one leg that's smaller and one that's larger, it would probably make sense to label this one as the larger one and this one as the smaller one. So we'll call this side length 7 centimeters and we'll call this one 4 centimeters. Now in order to define all 6 trigonometric functions, we also need to know the length of the hypotenuse. Well, if this is a right triangle and we have 2 side lengths, then we know all the sides are related by the Pythagorean Theorem. So we're going to end up using the Pythagorean Theorem here in order to solve for the remaining side, in this case the hypotenuse. The most important thing here is going to be to set up that Pythagorean relationship correctly. So if we have leg lengths and we're solving for the hypotenuse, we have to make sure we're plugging in these values into our function correctly. Or not our function, excuse me, our relationship. So one way of writing the Pythagorean theorem would be opposite squared plus adjacent squared is equal to hypotenuse squared. Now opposite, adjacent, how do we know which one is which here? Well, we've been told that we want to reference the smaller acute angle. The general relationship in a triangle is that the largest angle will be opposite the largest side, and the smallest angle will be opposite the smallest side, and then the one in the middle behaves the same way. So large angle, large side, small angle, small side. So since this is going to be the smallest side, this is going to be the angle that we're going to think of as theta. So if this is where theta is being placed, we know this is going to be the opposite side. It's opposite of theta. And this will be the adjacent side since it's the leg that's incident with theta. And of course it's not the hypotenuse. So opposite here is going to be 4 centimeters. So 4 centimeters squared. Adjacent is 7 centimeters. So 7 centimeters squared. And then hypotenuse is our unknown. It's what we want to solve for. Okay, so now we need to square. So that's going to be 16 square centimeters. Then 7 squared is going to give us 49. So 49 square centimeters. And that is equal to hypotenuse squared. So add these together, and if you need, use the calculator. The last thing you want is to make a mistake based on just arithmetic, so just verify. So 16 plus 49 is going to give us 65. So 65 square centimeters is equal to hypotenuse squared. Now we need to solve for just the hypotenuse, so we're going to take the square root of both sides, which is going to isolate our h. And whenever we take a square root in an equation, we need plus minus on the other side in order to indicate that both a positive and a negative could be squared to take us back to a positive output. So it's going to be plus or minus square root of 65, and then we also take the square root of our units, so that's going to give us centimeters. Now we need to simplify this radical as much as we can, so that's going to be a skill we use a lot in trigonometry, simplifying radicals. How do we know if this can be simplified? Well, is 65 a perfect square? That's a good place to start. So let's see. If I take the square root of 65, what do I get? Okay, I get a number like this, which means ultimately square root of 65 is an irrational number. In other words, we can't completely simplify it, but maybe we can simplify it in part. So if we can't take the square root of 65 exactly, is there something that divides into 65 that we can take the square root of? What would that look like? Well, what we're looking for here are any perfect squares that would divide into 65. So our perfect squares are going to be 4 and 9 and 16, 25, 36, 49, so on and so forth. We're looking at those kinds of numbers. If any of those numbers divide into 65, then we can break 65 up into factors, take the square root of the perfect square, and then leave whatever's left over. So do any of those numbers divide in? Well, 65 doesn't look like it's divisible by 4. 65 divided by 9, that's not going to work. Delete, clear. 65 divided by 16. Well, if it doesn't divide in by 4, then it won't divide by 16. What about 25? 65 divided by 25. That's not going to work. 65 divided by 36. Well, 36 is more than halfway to 65. So at that point, we know we can stop, and we know nothing else is going to divide in. So none of our perfect squares are going to divide into 65. So what that tells us then is that square root of 65, that's as simple as we're going to go. Now what about the plus minus issue here? How do we know which one, if either, actually represents the length of our hypotenuse? Well, we have to think about the context of the problem. We're talking about an actual physical triangle in space. Like imagine just drawing this triangle on a sheet of paper or drawing it on the ground. If we have a physical triangle, that means it has to have positive side lengths. So in this case, in the context of this problem, the only length that makes sense is going to be the positive root 65 centimeters. We'll talk about what it means if the length is negative, maybe not for the hypotenuse, but in other situations, we will use the negative value. But if we're talking about a physical triangle in space, all the side lengths are going to be positive. So the length of our hypotenuse is going to be root 65 centimeters. So once we have the full triangle filled out, we know all the side lengths, we know where the angle is that we're evaluating in each of these trigonometric functions, we have enough information to find all of these values. So just as a reminder, our acronym, so, ca, TOA, that's going to give us the information we need to label these three ratios. So sine is defined as the opposite side divided by the hypotenuse. So the opposite side divided by the hypotenuse. Now before I write it in here, I'm going to take it down here and I'm going to do a little bit of work with that ratio. So sine of theta is defined as the opposite divided by the hypotenuse. So that's going to be 4 centimeters divided by root 65 centimeters. Now before we actually do anything with these numbers, I want you to notice something, and then we're never going to worry about this again. Notice when we take the ratio of these side lengths, we have a common unit in the numerator and denominator, which means not only do these values divide out, but the unit divides out as well. Which means what we're left with now is a constant that is unitless. So whenever we take a trigonometric ratio, any trig ratio, what's going to happen is that when we take that ratio, because we're dividing a length by another length, those units are going to cancel, and what we're going to be left with is just a constant without any unit. So our trigonometric values, our trigonometric ratios, are actually unitless. So what that also means is that these units at the end of the day are not going to matter. If these were all feet or maybe miles or light years, whatever you wanted them to be, these ratio values would be the same. So units at the end of the day are not going to matter when we're evaluating these different trigonometric ratios. So we're not going to worry about the units from here on out as long as we know all the units are the same for each of the lengths in our triangle. So what we now have is 4 over the square root of 65. Now we're going to go back to this direction to rationalize the denominators. Rationalizing a denominator means if we have a radical in the denominator, we want to convert this ratio to a form that will no longer have this radical in the denominator. So the general rule here to rationalize is that we're going to multiply top and bottom by whatever the square root is that we want to rationalize. So I'm going to multiply in the denominator by root 65, and I'll show you why in just a moment. But if I do it to the denominator, I have to do it to the numerator as well, which keeps everything in balance. Ultimately, we're just multiplying by 1. Anything divided by itself is just 1. So although we may change the structure of this expression, we're not changing its meaning because all we're doing is multiplying by 1. So what's the benefit of doing this? Well, in the numerator, we can just multiply straight across. So 4 times the square root of 65 is just 4 root 65. The 4 does not distribute into the radical. It stays outside. This is rational. This is irrational. In the denominator, that's where we really want to focus on what's happening. So we have root 65 and then another root 65. So if we were to multiply these two values together, we have the square root of 65, but it's now squared. So what would happen if we take the square root of 65 and square it? Well, squaring and taking a square root are going to be inverse operations. So the benefit of doing this right here is that the square root is eliminated. By taking this root 65, multiplying it by itself, that square root squared, the square and the square root cancel out, and we're just left with the radicand, in this case 65. This is going to be the value that we'll report as our value for sine. This is going to be the rationalized value for our sine function. So the sine is defined as 4 root 65 over 65. Now before we go to cosine, it may be helpful to go ahead and find the cosecant. Sine and cosecant are reciprocals. So if sine is the opposite over the hypotenuse, then cosecant is defined as the hypotenuse over the opposite. So hypotenuse over opposite is going to be root 65 over 4. And notice that one's already rationalized. We don't have a radical in that denominator, so we don't have to do anything with that one. Now suppose you used this value for sine and then took the reciprocal of that. Well, if you take the reciprocal of that to find your cosecant, the reciprocal is going to have a radical in the denominator, which means you then have to rationalize again. So that is an argument for taking an extra step and actually writing out how you rationalize your particular trig value. If you were to look at this version of sine and then take its reciprocal, well, that's going to give you this rationalized version of cosecant. So there are a lot of different strategies to find your different trig values, and over time you're going to find what works best for you. Ultimately what you're going to want is whatever saves you the most time. Now let's look at the cosine. So cosine is defined as adjacent over hypotenuse. So the adjacent side divided by the hypotenuse. So cosine of theta is defined as the adjacent, which is 7 centimeters, divided by the hypotenuse, which is root 65. Now remember, the units are going to cancel out, so we're not going to worry about the units from here on out. Now this also needs to be rationalized. Same strategy. So we're going to take the square root of 65, multiply in the numerator and denominator, whatever the radical happens to be that we want to rationalize. And so our numerator becomes 7 root 65, and then root 65 now squared. A square and a square root are inverses, so that's now rationalized. So 7 root 65 over 65. It's also worth mentioning that potentially we may have a common factor among the rational parts of this expression. So 4 and 65 or 7 and 65. If we do want to divide that out before we report our final answer. In this case, we don't have any common factors, so we don't need to worry about that. So 7 root 65 over 65. Secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, secant will be hypotenuse over adjacent. So root 65 over the adjacent side, which is going to be 7. And then tangent, we've got a couple different options for tangent. Tangent could be opposite over adjacent. So opposite over adjacent. Well, notice neither of those sides involve a radical length at all. So we can immediately report that one as being already rationalized. So opposite over adjacent is going to be 4 over 7. And then again, cotangent is going to be the reciprocal. So adjacent over opposite, which is going to be 7 over 4. And that's going to give us all of our trigonometric values. Let's look at another example. So in this one, we had leg lengths, 2 leg lengths. Let's do one with slightly different information. So suppose our right triangle has a leg of length 5 root 3 inches, and its hypotenuse has a length of 2 root 21 inches. We want to, again, evaluate our 6 trig functions for the smaller acute angle, and then rationalize as necessary. Now we automatically know where the hypotenuse is going to have to go, so 2 root 21 inches, if we're going to label that, that's 2 root 21 inches. Now 5 root 3 inches, is that the long side? Is it the short side? Well, at the end of the day, ultimately we don't know. And I don't want to label the particular angle in question, which angle we're going to use, until we know what the other side length is. So for now, 5 root 3, we're just going to pick one of the legs and we're going to label that. So let's just label this side as 5 root 3 inches. Okay, so is this truly the longer leg or is it the shorter leg? We're not going to know until we solve for the other leg length. So for now, we're just going to label it and then we'll go from there. Now we need to find the other leg length. Now again, we don't know, is this truly the adjacent side that we know? Is it the opposite side that we know based on the actual angle we're going to use? So we can just use generic Pythagorean theorem. That's perfectly fine. So a squared plus b squared is equal to c squared. This could be a or it could be b, your choice, doesn't matter. So let's call it a. So 5 root 3 inches squared plus b squared is equal to the hypotenuse length squared. So 2 root 21, and again, it's squared. Now, be careful as you simplify each of these exponents. We have to square both the rational and the irrational part. So we're going to square the 5, which gives us 25. And then if we square the square root of 3, that's going to eliminate the radical and leave us with a 3. So 25 times 3 is going to give us 75. So 75 plus b squared. And then same thing over here. So square our 2, that's going to give us a 4. Square the square root of 21, which is going to give us 21. So 4 times 21, let's just verify what that is. So 4 times 21 is going to give us 84. So that's going to be 84. Now I need to isolate this term. So subtract 75. So 84 minus 75 is going to give me 9. So that means b, if we take the square root of both sides, b is going to be plus or minus square root of 9, which equals plus or minus square root of 3. Now again, we're talking about a physical context, so that means we're going to take the positive version. So this is going to be 3 inches. Now based on that, which side is shorter, which side is longer? Is this the angle we want? Is this the angle we want? Well, we need to know 5 root 3 or 3, which one is going to be larger, which one's going to be smaller. Well, if root 3 is greater than 1, which we can definitely say it is, then we're taking 5 and multiplying it by something greater than 1. So this value is going to be bigger than 3. We can also verify that with the calculator. So if you were to take 5 and multiply it by the square root of 3, that's going to give you about 8.7. So this is about 8.7 inches, and this is 3 inches. So this is going to be the smaller side of the two, which means it's going to be opposite the smaller angle. And we were told we want to evaluate for the smaller acute angle. So this is truly going to be where we label theta. Now what if I had put 5 root 3 down here to begin with? How would this change things? Well, we would have to label this side as 3, and even though it looks longer than the side we already labeled, we have to label the angle in relation to the actual side labels. So keep in mind, this little generic right triangle is not to scale. It's just a diagram to help us label what we know. We have to label our angles in relation to how we've labeled our sides, whether we've truly put them in the order that we would just based on the scale of the triangle or not. So you need to be very careful with that kind of thing. Longest side, opposite largest angle. Smallest side, also opposite smallest angle. Now we have everything we need in order to find all our ratios, so let's go through and find all of those. So remember, katoa, I'm going to write it up here one more time. Katoa. Okay, so sine is defined as opposite over hypotenuse. Okay. So let's go down and let's simplify that. The sine of our angle is the opposite side, which has a length of 3 inches, divided by our hypotenuse, which has a length of 2 root 21 inches. Okay, we need to rationalize this. Now with the previous problem we did, the denominator only had a radical component. It didn't have something that was rational as part of it. When we rationalize, the only thing we need to multiply by is what we actually want to rationalize, which is the actual radical part. So we don't have to multiply in the denominator by 2 root 21. We're just going to multiply by root 21, just the radical that we want to eliminate. And so in the denominator, the root 21 and root 21, well, we're now squaring the square root, so the square root goes away and we're just left with a 21. But don't forget that we still have that 2 right there. So you have to be very careful as you simplify something like this. So in the numerator, we have 3 root 21. And in the denominator, we still have the 2. And we also have the 21 that we got from the rationalization. Now this can still be simplified because look at these two rational parts. We have a 3 in the numerator, a 21 in the denominator, and they have a common factor. 3 divides into both of those. So 3 divides into 3 1 time, and 3 divides into 21 7 times. And that's going to give us our simplified value. So in the numerator, now we just have root 21, and in the denominator we have 2 times 7, which is going to give us 14. So that is going to be the rationalized value of our sine. So root 21 divided by 14. Well, if we know the sine, we can find the cosecant. If sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So hypotenuse over opposite, that's going to be 2 root 21 divided by 3. Now what about the cosine? Adjacent over hypotenuse, so 5 root 3 over 2 root 21. Now this one's going to be interesting. Notice both of these values we're using have radicals. So simplifying this is definitely going to be a little bit more interesting. So adjacent is 5 root 3. Hypotenuse is 2 root 21. Now we can approach simplifying this in a couple of different ways. At the end of the day, we want something that's fully simplified. Anything that can be divided out has been divided out, and we know we want to get rid of the radical in the denominator. So without any other ideas of what to do, let's just focus on the rationalization. So same idea as before, we need to get rid of that root 21. So I'm going to multiply in the numerator and in the denominator by root 21. Okay, so in the numerator, we now have 5 times root 3 times root 21. Now the two radicals can be combined together under one square root. So we now have both a 3 and a 21 under that radical, which is going to give me, if I'm not mistaken, 63, root 63, that looks right. And then what do we have in the denominator? Well, 2 is still there. And then we rationalized the square root of 21, which now gives us a 21 just as is. Now notice the radical in the numerator changed. We went from 2 radicals that were fully simplified, that we couldn't divide anything out of, to a new radical. So we need to verify that we can't do anything with that root 63 potentially. So same kind of thing as before. We want to verify, is there anything that divides into 63 that we could take the square root of? Well, one that comes to mind is going to be 9. 9 divides evenly into 63, and 9 is a perfect square. So I'm going to take that root 63, and I'm going to split the 63 up into a 9 and a 7. And I'll just leave it as 2 times 21 in the denominator. So the benefit of doing that is now this 9, we can take the square root of 9 even though we can't do anything with that 7 under there. So I'm going to take the square root of 9, which is 3, and so now my numerator has a rational 5, a rational 3, and then just the square root of 7. And then my denominator still has the 2 and the 21. Now I need to look at these rational parts. This radical is fully simplified. I don't have any more radicals in the denominator, but I need to look at everything that's rational. So 5, 2, 5, 21, those don't have anything in common. 3 and 2 don't. 3 and 21 do have a factor of 3 in common. So I'm going to divide that out. So 3 divides into 3 one time. 3 divides into 21 7 times. And so that should give me my fully simplified numerator and denominator. So 5 times 1 times the square root of 7 is going to be 5 root 7. And then 2 times 7 is going to give me 14. So that is going to be my value for cosine. 5 root 7 divided by 14. Now what about my secant? Again, I need to take the reciprocal. So if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. Okay, so if I were to just take this reciprocal right here, that would give me the non-simplified value of secant. Here's another option though. So notice if I just took the reciprocal here, which would literally be hypotenuse over adjacent, I would still have this issue with 2 radicals. What if I just took the reciprocal right here though? The benefit of taking the reciprocal of this form is that this form only has 1 radical. We've already taken care of that double radical issue. So in this case, that might be a better option to truly just take the reciprocal of our cosine in order to find the secant. So let's do that and let's see if that saves us a little bit of time. So secant theta is not only hypotenuse over adjacent, but it's also just the reciprocal of whatever our cosine is. So the reciprocal of our cosine in this case is going to be 14 over 5 root 7. Now again, I need to rationalize that square root of 7. So I'm going to multiply top and bottom by the square root of 7. And then numerator becomes 14 root 7. And then the denominator, we have our 5, and then we now have a rationalized 7. Now 14 and 7 have a common factor of 7. So it divides in twice there, divides in once there. And so our simplified value is 2 root 7 over 5 times 1, which is 5. So that is going to be the value of our secant, 2 root 7 over 5. Okay, and then tangent and cotangent. So tangent is defined as opposite over adjacent. So opposite over adjacent. Now again, it looks like we're going to have to rationalize something. This is definitely a test of your preliminary algebra skills, right? So opposite over adjacent. So 3 over 5 root 3. Rationalize the square root of 3 in the denominator. So we're multiplying by root 3 over root 3. The numerator is going to be 3 root 3. In the denominator we have our 5, and we now have that rationalized 3. We have that common factor among the rational parts. So that is eliminated, and both of those just go to 1. So that means our new numerator is going to be root 3, and our denominator is going to be 5. So the tangent value is going to be root 3 over 5. And then cotangent will be adjacent over opposite. So adjacent over opposite. And so it turns out that's already rationalized in that form. So cotangent is going to be 5 root 3 over 3. There we go. So a little bit more involved with this particular problem in order to get all of those values, just based on the fact that our actual side lengths are not really nice, pretty numbers. If you were going to use trigonometric concepts in real life, more than likely you're going to run into these kinds of values. It's not always going to be really pretty numbers when you're looking at real-world type problems. So unfortunately, this kind of algebra is realistic. Now that being said, in the cases where only one of the 3 sides has a radical component to its length, typically the rationalization will not be this involved. And it'll also get to the point where you can potentially do some of the rationalization in your head. You'll get used to this pattern of multiplying numerator and denominator by that radical, and some of the rationalization you may be able to do without having to write down all the extra work. So let's look at another example. So for these previous two, we were given actual side lengths, either a pair of legs or a leg and a hypotenuse. We can also be given information about our triangle and its angle measures through other trigonometric values. So if we're given one of the trigonometric values for our triangle, that also gives us a different way to label the sides of the triangle. So in this case, suppose that secant of theta is defined as 3 over 2 for the acute angle theta. And we don't know anything specific about theta except that this is the value of its secant. We want to evaluate the other trig functions for theta, and again rationalize our denominators if necessary. So notice again, it doesn't say anything about theta is the smaller angle or theta is the larger angle. All we know is that theta has a secant of 3 over 2. So that means we can technically put theta wherever we want as long as we choose one of the acute angles. So just for the sake of being different, let's put it down here. Now once we choose where the angle goes, we have to label using this trigonometric value in relation to where we've labeled the angle. So secant is related to cosine. Remember, cosine is defined as adjacent over hypotenuse. So that means the secant is defined as the hypotenuse over the adjacent. So when we've been given this ratio 3 over 2, we've been given 2 side lengths for this triangle. Specifically, we've been given the hypotenuse and the adjacent. So the hypotenuse has a length of 3 units, and the adjacent has a length of 2. Now notice, because we've been given an actual trig value as opposed to leg lengths or the hypotenuse's length, we don't know anything about units. Because remember, when we found the trig values, the unit in the numerator and denominator ended up canceling out. The same kind of thing has happened here. So we don't know if we're talking about 3 and 2 inches or 3 and 2 feet. At the end of the day, we don't know. But if the idea is that we're just finding trigonometric ratios, all of those ratios are going to be unitless anyway. So knowing the units in our actual triangle is not important if the goal is just to find these trig ratio values. All we need to know is what are the actual numbers and where do they go in relation to our angle in this right triangle. So we have the hypotenuse and we have one of the legs. We need the other leg. In this case, it will be the opposite based on the fact that we were given secant. So we know that the opposite squared, which is what we don't know opposite, plus the adjacent squared is equal to the hypotenuse squared. So based on Pythagorean Theorem, this will allow us to solve for our unknown side. So opposite squared plus 4 is equal to 9. So subtract our 4, move it over. So opposite squared is equal to 9 minus 4, which is 5. And we take the square root. So opposite is equal to plus or minus root 5. Now why do I keep putting plus or minus if, again, everything is in the context of a triangle and it's always going to be positive? I want to do this because I want you to get into the habit of it now. When we take it out of this context and look at things a little bit more broadly, we do have to worry about this issue with positives or negatives. So even though our side lengths are all positive numbers right now, that will not always be the case. So we do need to worry about this issue with plus or minus in general. Well, now that we have all of our side lengths, we have everything we need to label our triangle. So sine is defined as our opposite over our hypotenuse. So opposite over hypotenuse, that's already going to be rationalized. So root 5 over 3. Now cosecant is going to be the reciprocal of that. And let's see if we can just rationalize this one mentally. What's going to happen with this one when we rationalize? So there's the non-rationalized version. If we rationalize, essentially the pattern is that the radical moves to the numerator, and then the radical itself drops off and we're just left with the radicand in the denominator. So the rationalized version will be 3 root 5 over 5. And if you need to, take a moment and actually write this down, rationalize it by hand, or if doing it like this makes sense to you, that's perfectly fine as well. Okay, cosine is the reciprocal of secant. So if secant is hypotenuse over adjacent, then cosine is going to be adjacent over hypotenuse. So the reciprocal of that, which is 2 over 3. And then tangent, let's actually go about finding tangent a different way this time. We can find it using our ratios, or if we know the sine and cosine, tangent is also defined as the ratio of sine over cosine. So let's actually use the identity here and see if we can find tangent that way, and then maybe just verify it using the ratios. So another way to evaluate tangent is using the fact that tangent is defined as sine of theta divided by cosine of theta. Well, we know what those values are. Sine of theta, rationalized, is root 5 over 3, and cosine is defined as 2 over 3. So we have one fraction divided by the other. If we want to convert to multiplication, we can do that. So that's going to be root 5 over 3 times the reciprocal of 2/3, which is going to be 3/2. And so our 3's cancel out, and we're left with root 5 over 2 is our value for tangent. So tangent is going to be the square root of 5 over 2. Does that also match up with our ratios? Well, tangent is defined as opposite over adjacent. So from this angle, opposite over adjacent is going to be root 5 over 2, which is what we have for our tangent. So that makes sense. Now let's see if we can do the same thing for cotangent. Another way of defining cotangent is the ratio of cosine over sine. So we'll flip this one. So cotangent of theta is defined as cosine theta divided by sine theta. And we know that cosine theta is 2/3. And we know that sine theta is root 5 over 3. Again, we're dividing by a fraction, which is the same thing as multiplying by its reciprocal. So we take the reciprocal of root 5 over 3, and that's going to be 3 over root 5. So our 3's are going to be eliminated. So that's going to give us 2 over root 5. And we need to rationalize that, and that's going to be 2 root 5 over 5. So that will be our value for cotangent. Does that again gel with our ratios? Well, cotangent, if tangent is opposite over adjacent, cotangent is adjacent over opposite. So 2 over root 5, which will take us right there. And then again, the rationalization is going to take us to this value. So maybe this is not a time saver here, but it's good to start getting into this mindset early on of how all of these ratios are related to just the sine and cosine. Once we get a little bit further into how these trigonometric functions are defined, there will be certain situations where sine and cosine will be very easy to find, but the other functions won't necessarily be easy to find. So if we can determine how all of these are related to sine and cosine, it's typically going to be a good time saver. So using this relationship among tangent, sine and cosine, and then cotangent, sine and cosine, is going to potentially be valuable in the future. So the last thing, let's look at another one. Use another ratio. And then we need to talk about what happens when our angle is actually known. So one thing I want you to notice at this moment is we don't actually know what our angles are. Aside from the fact that we're in a right triangle and we know we have a right angle and two acute angles, we don't know any of the actual angle measures. What happens if we do know the angle measure? How does trigonometry work in that respect? Well, we'll talk about that just a moment. So let's do one with another actual ratio, label our triangle, and then go from there. If you want, you might want to pause the video and see if you can work through this one, and then go back through and watch and check your answers. So we know tangent theta is root 15 over 9 for some acute angle theta. And again, we want to evaluate our other functions and rationalize if necessary. So it doesn't matter where we put theta, but again, I'm just going to put it here just for some variety. So tangent is opposite over adjacent. So that means our opposite is going to be root 15. Our adjacent is going to be 9. And so we need our hypotenuse length. So that means root 15 squared plus 9 squared is equal to our hypotenuse squared. Now when we square root 15, that just rationalizes it. And then 9 squared is going to be 81. And that's equal to our hypotenuse squared. So hypotenuse squared is equal to 15 plus 81, which is going to be 96. We take our square root. So h is equal to the positive or negative square root of 96. Now can we simplify this one? 96 is not a perfect square, but is there a perfect square that divides into it? That's a good question to ask. Well, as it turns out, 4 divides in, but so does 16. We can actually divide 16 into 96. So we can take this radical and we can split it up into the square root of 16 and the other necessary factor, which is 6. And then we take the square root of 16, which is going to be 4, and we can leave root 6 since it can't be simplified any further. So that means this side length is going to be positive for root 6. Now looking at this initially, it may seem like maybe we've labeled things incorrectly. The longest side is supposed to be the hypotenuse, correct? Well, this is root 15. Remember, 4 root 6 is really the same thing as root 96. So root 15 versus root 96, this is definitely going to be the longer side. And what about in relation to 9? Well, 4 times the root square root of 6, let's see what that is. 4 times the square root of 6 is more than 9. So it does in fact define the longest side in our triangle. So now let's find our ratios. So sine is defined as our opposite over hypotenuse. So we're definitely going to need to work this rationalization out. So opposite over hypotenuse. Again, we need to multiply top and bottom by root 6. So root 15 times root 6, well, they're both going to combine under that single radical. So 15 times 6 is going to be 90. So that's going to become the square root of 90. And then our denominator, we have 4, and then we have that rationalized 6. Now, can we simplify anything related to the square root of 90? Well, again, 90 is not a perfect square, but 9 divides in. And the square root of 9 is going to be 3. So that simplifies to 3 with that root 10 left over. And then our denominator is going to be 24, or you can leave it as 4 and 6 if you want. Now we can simplify that common factor of 3. So 3 divides into itself 1 time. It divides into 24 8 times. So that means our sine has a value of root 10 over 8. Okay, cosecant is going to be the reciprocal of that. So we can either do hypotenuse over opposite, which again will put us kind of back where we are here, or maybe just use this version of the sine instead. So cosecant would be the reciprocal of sine, which is going to be 8 over root 10. Now again, we need to rationalize, so that's going to be 8 root 10 over 10. And now we again have a common factor. In this case, the common factor is 2, leaving us with 4 over 5. So that's going to be 4 root 10 over 5 for our cosecant. Now what about cosine? That's going to be adjacent over hypotenuse. So our cosine of theta is going to be the adjacent, which is 9, divided by our hypotenuse, which is 4 root 6. Okay, rationalizing, that's going to be 9 root 6 divided by 4 times 6. 9 and 6 have a common factor of 3. And so we're left with a 3 in the numerator and a 2 in the denominator, which is going to give us 3 root 6 divided by 8 for our cosine. Now secant is the reciprocal of cosine, so hypotenuse over adjacent, and as it turns out that one's already rationalized. So 4 root 6 over 9. We know our tangent. Our cotangent is the reciprocal of that, so adjacent over opposite. So our cotangent of theta is the adjacent, which is 9, divided by the opposite, which is root 15. Again, rationalize. So 9 root 15 over 15. 9 and 15 have a common factor of 3. And so that's going to give us 3 root 15 over 5. And that's going to be all 6 of our values. And again, notice in this situation, because 2 of our side lengths had actual radical parts to them, the rationalization was a little bit more involved. So in situations like that, it is a good idea to write down at least some of the steps you take towards rationalization. Try not to do too much of it in your head at that point, just because there are going to be a couple steps involved in rationalization. So the last thing we're going to talk about is, again, what happens when you actually do have a known angle. What do these trigonometric values look like when you have a known angle? So all of the problems we looked at so far, we had this unknown angle measure, and maybe we knew information about the sides of the triangle that contain that angle, or maybe we know something about one of the trigonometric values for that angle. In other words, we can draw a right triangle and label it based on how the side lengths relate to the particular angle in question. That's not always going to be the case. So sometimes we're going to know the angle rather than the side lengths. Sometimes we know the side lengths instead of the angle. Sometimes we know the angle instead of the side lengths. Now, if we know the actual angle itself, we're going to take a couple different approaches to finding these trigonometric values. What are they going to be if we know what the actual angle is but don't know anything about a triangle that might contain that angle? Well, depending upon the angles we have, some of the angles will actually memorize what the trigonometric values are, but only for very special cases. For just your generic angles, if the goal is to just get an approximation of what the trig values are, maybe in the context of some type of applied problem, typically we're just going to use a calculator in order to approximate our trigonometric values. If we're going to use a calculator, the big thing we have to be careful about is we must be aware of the type of angle measure being used. Remember, we talked about a couple different types of units used for angle measure. So we've used degrees, 2 different versions of degrees technically, and then we also talked about radians. So your calculator can handle degrees and it can handle radians, but it needs to know which angle measure you're using in any particular situation. So this is where the mode button is going to be helpful. So if you look at your calculator, let me clear everything out. If you look at your calculator right next to secant, it says mode. And if you click on that, there's a lot of options, but one of the options, in my case, it's the 4th row down. It says radians, which is currently highlighted on my calculator, and then it also says degree. This is where you're going to change the angle measure mode in your calculator in order to evaluate your trigonometric functions correctly. So if your angle is given in radians, you want to make sure radians is highlighted. If your angle is given in degrees, you want to make sure degrees is highlighted. So for the first two parts of this particular example, we want to use our calculator to approximate our function values, rounding to 4 decimal places. For the first two, we have angles given in degrees. So we'll want to make sure our calculator is in degree mode. So I'm going to use the arrows to scroll down, highlight the mode we want if you need to change from radians to degrees, highlight it and then press enter, and it will select that mode for you. Now once you've selected that, you can just use clear to get out, and it's set that as the particular mode in question. So in this case, for the first one, we want to evaluate tangent for the angle 55.73 degrees. So right across from clear, diagonal from clear, you have 3 buttons. One says sine, one says cosine, one says tangent. You also have some little things above in blue. We'll talk about what those are later, but I also want to talk about in just a moment what they are not. So sine, cosine, and tangent, you already have buttons for those. In this case, we want tangent. So I'm going to hit the tangent button first, and then I know I'm in degree mode, so I'm just going to type in the degree measure for this angle, which is 55.73 degrees. And it's not going to put a degree symbol, but your calculator knows that it's intended to be in degrees. And so once I have that typed in, I can just press enter, and that's going to give me the trigonometric value. So notice it's not given as an actual ratio because we don't actually have a triangle with actual side lengths, but it is giving me the value that that ratio would have if we were to evaluate it in an actual triangle. So to 4 decimal places, it's going to be 1.4676. Okay, now next one, secant. Here's where we're going to have to be careful. So we don't have a secant button. As it turns out, we don't have a secant button. What we do have are sine, cosine, and tangent. So knowing those reciprocal relationships is going to be very important here when the goal is to use a calculator and get some approximations. So we know that secant is defined as the reciprocal of cosine. So if we can use cosine, we can find secant. Now here's again where we're going to have to be careful. Right above cosine, it says cosine with a superscript of -1. Now you may be aware that in some cases a superscript of -1 means take the reciprocal. And so looking at that, you may think, okay, well that's going to be secant, right? Because that means we're going to take the reciprocal of cosine, which is secant. That is not the case in this situation. So those blue notations, sine, cosine, and tangent with that superscript of -1, those do not actually represent the reciprocal functions. They actually represent what we call inverse trig functions, which are different. We'll talk about those a little bit later. But they don't represent the reciprocal functions cosecant, secant, and cotangent. So if you want to find a secant value, or cosecant or cotangent, you're going to have to actually write an expression for the reciprocal. So if secant is defined as the reciprocal of cosine, the way we indicate that is by doing 1 divided by cosine. That's the way we write out an actual reciprocal. So if we want secant, it's going to be 1 divided by cosine. And my angle measure is 46.3 degrees. So that's going to be the way we evaluate a secant, 1 divided by cosine. So in this case, the value comes out to 1.4474, roughly. 1.4474. Okay, now what if our angles are given in radian measures? So for the last two, how do we know they're in radian measure? Well, the pi, unfortunately, does not give it away. What gives it away is the fact that we don't have the degree symbol. So anytime we have an angle measure and we don't have a degree symbol, it's understood that regardless of what the number is, whether there's a pi or not, that that angle measure is given in radians. So for part C and D, we need to go ahead and convert to radian mode. So go into mode, and then again, you want to go down to the option for angle measure, and we're going to change back to radian mode. So degrees are currently highlighted. I want to scroll over radians and then hit enter. And that's going to put us in radian mode and then clear to get out of that. So first thing I want is the cosine of 2 pi over 7. So cosine, and then we can just literally type 2 pi divided by 7 and it understands what we want. And then I'm going to hit enter. So 0.62 0.235 roughly. Okay, and then last but not least, cosecant of 0.92, is that degrees or radians? Well, there's no degree symbol, so it's understood to be radians. Now again, we don't have a cosecant button. That sign with a superscript of -1 is not cosecant. Cosecant is defined as the reciprocal of sine. So if we want a cosecant, we have to actually evaluate 1 divided by the sine of whatever our angle measure is. In this case, 0.92 radians. So there we go. So roughly 1.2569. And there we go. So we're going to run into all of these different situations throughout our study of trigonometry. Sometimes we'll have information about how we would label a right triangle, which is going to be beneficial because all of our trigonometric functions are labeled. They're all described in relation to the sides of a right triangle. Sometimes we'll know the actual angle measure. In the case of knowing the actual angle measure, either we can use a calculator to evaluate our trigonometric functions, get those output values, or as we're going to find out a little bit later, for special angles, things that we run into a lot as we consider different common angle measures, we're going to have some other strategies for finding those particular values.